Rates of chemical changes. Chemical reactions like these down here can occur at different speeds. Some are very, very fast and some are very, very slow, like the rusting of a nail. But there are several things that get these chemical reactions going faster. In general, these things right here promote faster chemical changes, higher temperatures, more surface area, kind of like if you crush something up, it would dissolve faster and promote a chemical change quicker, higher pressure, and these big bulky molecules just don't seem to change as quickly as the smaller ones do. Okay, kind of now to the meat of this. Catalyst is a term you'll need to know. Catalysts speed up the reactions. Now, they're not what's on either side of the arrows. These are outside forces that help speed up the reactions. Now, we have catalysts that can happen in our bodies. We have catalysts that occur outside of our bodies. And there are lots of different things that are catalysts. The process we use to make crude oil, the process we use to make ammonia, the process used to make plastics, even a process, a catalyst in our car to speed up the car exhaust. There is also something called an inhibitor. An inhibitor is, well, pretty much the opposite of a catalyst. A catalyst will speed up a reaction, whereas an inhibitor will slow down a reaction. So catalysts speed up, inhibitors slow down. Let's talk about what an enzyme is. An enzyme is a catalyst inside our body. These are proteins that act as catalysts inside our body for digestion, for example. There are several enzymes that help in digestion. Even in our saliva contains enzymes that help with our digestion. Enzymes even in the DNA chain of amino acids that help with the replication, with the production of DNA and proteins. Now let me tell you what a substrate is. A substrate is a material that an enzyme decomposes. Let me find my pen here and see if we can have an example here. You may remember when something decomposes, it kind of has that AB yields A plus B. So let's use hydrogen peroxide, for example. In fact, I don't think I have this balanced yet. Well, let's have hydrogen peroxide forming into H2O, and we'd have to have a 2 here. I believe we'll have to have a 2 here. There is an enzyme which in our body which decomposes this. So the substrate is the material an enzyme decomposes. So the substrate is the hydrogen peroxide. The hydrogen peroxide is the material that is decomposed. So that is the substrate. Some chemical equations, on kind of a different note but in the same section, some chemical equations are reversible. Now, whenever we had a chemical equation like this, we had one arrow pointing this way. We said it represented yields. So what is happening is this product, or this reactant, is turning into these products. But in reality, there are some chemical equations which go this way and then go back this way, forming again their reactants. And whenever you have that, you have these two arrows like this. You have arrow going one way, arrow going another way. So you can see this example. We have calcium CO3, which is a polyatomic ion, I do believe, which is being broken down, and CaO plus carbon dioxide is what this happens to be. The term that we often use whenever we have these kinds of reversible chemical equations is equilibrium. Now you've probably heard of equilibrium. It comes from the word equal, or at least they have the same prefix. Equilibrium kind of refers to the balance that you have to have in these equations, because whenever you have some instances, all these products are more, all these elements are more on this side of the equation, and some instances it's more on this kind of equation, kind of like a seesaw. Under certain circumstances, you have the weight, not the weight, but the more products over here. In some circumstances, you have that. But it's not the same balance. I mean, it's not like you go one way, then the other, one way, then the other. There are some factors which determine which side of the equation it's going toward. And it's going to be some of these parts right here. One of them is higher temperatures. Many of these reactions that go back and forth, the higher the temperature, the more it goes to the product side. The hotter it is, the more decomposition, I guess you might say. So if you then have less heat, then the more the equation would go back to this side. It would turn, these products would turn back in to the reactants with the less heat. Now, heat is just an example, but it does seem to turn out that way. Now, having this equilibrium in the first place, but amongst temperatures, it can also be amongst, for example, how much pressure. Higher pressure, it would go one way, lower pressure would go other. This is an example of Le Chatelier's principle. Just this fact that you have this equilibrium, and I'll read what Le Chatelier's principle is. If a change is made to a system, like this, in chemical equilibrium, the equilibrium shifts to oppose the change until a new equilibrium is reached. So whenever you have heat added, for example, then the equilibrium changes to one side. So whenever you don't have as much heat applied, then the equilibrium will kind of swing back, kind of like a balance, nature's balance, I guess you'd say, with chemical equations that happen to be like this. So let's take a look at these down here. Here's another one. I think this is ammonium here, ammonia, which is produced right here. But the principle is the reason the total amount of nitrogen and hydrogen yields ammonia, and why it goes back and forth with the amount of heat, the amount of pressure, and there's another thing besides heat and pressure, and it's not surface area, it's the amount of concentration. Now, when I say the amount of concentration, I'm not talking about how focused you are on the equation. It's you've heard of the word concentration when talking about like apple juice or orange juice. When you have a high concentration, you have a more juice itself and less water. So the amount of concentration you have, for example, in any given solution, say you have this ammonia here, which is just a small amount of ammonia in a large area, then it's not much concentration. So that might affect it producing more, or it might affect it producing less. So the temperature, the pressure, and the concentration kind of affect which way the arrows are actually going. And it's Le Chatelier's principle, which is the fact that it goes back and forth and kind of does, in fact, have that balance. Hey, I hope you learned a little bit about rates of change.